Ahí está grabando. Bueno, buenas tardes a todos. Estamos entonces empezando nuestro tercer día de conferencia. Entonces, bueno, ya han pasado la mañana los cursos, así que ahora es el turno de la conferencia plenaria de este miércoles. Nuestro orador va a ser Hiram Lopez, un gusto contar con él y poder presentarlo para el que no lo conoce. Hiram recibió el doctorado, el PhD en Simvestab, México, en el 2016, bajo la dirección del profesor Rafael Villarreal, que está por ahí. Durante el doctorado él estuvo en los años 2014 y 2015 en Suiza, bajo la dirección de Elisa Gorla. Y luego hizo un postdoctorado en los años 2016 al 2018 bajo la dirección de Felice Manganiello, o Felice Manganiello, en la Universidad de Clemson, en Estados Unidos. Y actualmente se encuentra, es un profesor asistente en Cleveland, Cleveland State University. Así que bueno, lo dejo con Hiram. Él nos va a hablar de códigos de red Euler. Dejo que él diga bien el nombre completo. Así que bueno, un placer presentarlo. Adelante, Hiram.
Muchas gracias, Ricardo. Muchas gracias por la introducción. Bueno, voy a hablar en inglés, si les parece bien. Si hay alguna duda, como siempre, en español o en inglés no hay ningún problema. Thank you very much, Ricardo, for the invitation. And the idea for today, I want to talk about augmented Reed-Muller codes. So augmented Reed-Muller codes, we are going to see why we have this definition, but the idea is that I wanted to focus on Reed-Muller codes because this is a family that it is well known, the Reed-Muller case. This work can be extended, and actually is already extended. We have another paper with the same people, with Gretchen and Daniel, about augmented Cartesian codes. But again, let's focus just on Reed-Muller because, well, this is something that people know. And the idea for today is there are not too many slides. I want that you keep a very simple idea, and I'm going to try to give up how you can prove some things, but just the idea is enough for today. If you are not very familiar with codes, well, and especially with evaluation codes. This is just the notation that we are going to use. We are going to have K as a finite field, and we have a linear code is just a subspace of K to the n. The length, as usual, is denoted by n. This is the number of entries that we have on every vector. The dimension is just the dimension as K vector space. And we are going to use the Hamming distance. And this is important because now there are other distances that have been studied. For that reason, well, I want to specify that we are using the Hamming distance. The minimum distance, the Hamming distance is just the number of coordinates where the vectors are different. Okay. And well, the dual. And what is the dual? Again, it is important to say that we are going to consider just the classical case, the Euclidean inner product. So the inner product, the inner product that everybody studied in high school. Well, it's not high school, in college. So we're going to study the inner product, and the dual is denoted by C perp. Okay, so this is just the classical notation for coding theory. And let's see what else we have. We have, well, today I want to talk about recovery. And what is the meaning of that? Well, on Monday, Cicero told something about this, about repair, how you can repair using Cartesian codes. But the idea is the following. So assume that you have data and you save all this data in servers. So in a few words, so all the entries, all the first entries of the vector are saved in the server number 1. All the second entries of the vectors are saved on the server number 2, and so on. Okay, so this means that every entry of the vectors are saved on one server. And the question is, if one of these servers fails, like here on this example, how can I recover this entry using the rest of the entries? So this is the classical problem for distributed storage systems using coding theory. And now one approach is the one that Cicero used on Monday. And this is coming from this, well, it's not coming from this paper. So this is a seminal paper, the Tamo bark construction. The Tamo bark says that, well, you can make codes in such a way that in order to recover this entry, you are going to use only a few other entries, okay? Not all the entries, because this is too expensive. So you are going to use only a few other entries. So these codes are called locally recoverable codes, because you can recover one entry using just a few other entries. And it's important for this case. If people know coding theory, well, maybe they know that coding theory can be used to recover recover the information that is transmitted. So in other words, usually we have errors. And on this case, we have erasures. It's not the same an error than an erasure. When you have errors, so this means that if you don't know where which entries are correct. When you want to correct errors, you need to know first which entries are not correct, and then you are going to recover those entries. When we have erasures, for instance, in this case, if we have this erasure, so this means that the rest of the entries are correct. So we don't have this entry, but at least we know that the rest are correct. So this is something important. So we have erasures. And as I said before, the Cartesian codes, well, this is a family, just think about the Ring-Muller codes, can be used to locally recover these entries. This is one approach. The approach that we're going to study today is coming from the seminal paper of Gurusgami and Gutters. And the idea for them is that you are going to use the rest of the entries, all the rest of the entries, but you are not going to use all the entry. So imagine that every entry, so let's focus on this entry here on the corner. Imagine that this is an element of a field extension. Well, if you see this element as in the field extension, so this means that you can see this element as a linear combination of elements in a small field, right? So in this sense, we are going to use all the entries, but we're going to use only part of this information. Okay, so this is the idea for Gurusgami and Gutters, and we're going to study this. And we're going to say more about this in a few seconds, okay? But the idea is that we're going to use the second approach for distributed storage systems. And we're going to focus on evaluation codes. What is an evaluation code? Well, an evaluation code depends on a set of polynomials that you are going to evaluate and a set of points that you are going to use to evaluate. Okay, so for instance, not for instance, so you fix a set of points. This is important. So you fix a set of points, and now that the set of points is fixed, take one polynomial, any polynomial that you like, and evaluate this polynomial on this set of points. So the first entry is coming from the value of the polynomial on the first point. The second entry is coming from the value of the polynomial on the second point, and so on until the last entry, which is the value of the polynomial on the last point. So using this function, this is called the evaluation map or the evaluation function. And using this function, you can define the evaluation code that depends on a set of polynomials and a fixed set of points, which is something important that is something that is important for the evaluation codes is the vanishing ideal. And this is something well known in commutative algebra or algebra geometric. And what is the meaning of the evaluation of the vanishing ideal? Well, you are going to take all the polynomials that vanish on all the points at the same time. Okay, so this is how you can find the vanishing ideal. And then, so take a linear subspace of polynomials, L. So take a linear subspace of polynomials, and using this evaluation map, you are going to evaluate on all the points, on all the using all the polynomials of this linear subspace. Well, when you evaluate, the image of the evaluation map is called evaluation code. Okay, so the idea is that an evaluation code is coming when you evaluate a linear subspace of polynomials on a fixed set of points. I'm sorry. Okay, so this is how you find the evaluation code. What can we say? Well, this is just to refresh. So just remember, the evaluation code is the set of all vectors that you obtain when you evaluate all the polynomials of the linear subspace in all the points. Well, what are the parameters of this evaluation code in terms of these polynomials and in terms of this set of points? Because an evaluation code is coming just from a set of polynomials and a set of points, we need to be able to say something about the parameters of the code in terms of these two guys, the points and the polynomials. Well, the length of the code, the number of entries, is of course the number of points that you are using to evaluate. This is not too complicated, right? What about the dimension? Well, the dimension is coming from the space of polynomials that you are using. So you just need to find the dimension as k vector space, and is related to the polynomials. It's not exactly the same than the dimension of the polynomials, but it's related. It's not too complicated. The point is, the length depends on the points. The dimension depends on the polynomials. And the minimum distance depends on both guys. This looks too complicated, but it's not too complicated, it's just notation. And the important thing is, if you want to find the minimum distance of the evaluation code, well, what you need to do is you need to find the polynomial that has the maximum number of zeros on the set of points. Okay, so this is a reason why we can see that in general the minimum distance is harder, because the length depends on points, the dimension depends on polynomials, but the minimum distance depends on both guys, the points and the polynomials. Okay, so this is how you can find the parameters of an evaluation code in terms of the points and in terms of the polynomials. Just to fix some ideas, this is an example of when we take points in the plane. Well, we take these 3 points, so we fix these 3 points. And when you take a polynomial in 2 variables, because the points are in the plane, you evaluate this polynomial on these points. So in this case, we have 3 points, so you are going to obtain a vector with three entries. I'm sorry, a vector with 3 entries. So this is just to fix some ideas about the evaluation codes. And now, what about the dual? Well, this is a work that we just published with Ivan Soprunov and Professor Villarreal. And in this work, this is about the dual of evaluation codes. The important thing, one of the important things for this work is that if you take an evaluation code, the dual is also an evaluation code. But this is something interesting, because the dual is coming also from points and polynomials. But actually, for the points that you need to use to evaluate is exactly the same. So in other words, you take some polynomials and take some points and now make the evaluation code. Well, if you want to find the dual, you are going to use exactly the same points. Of course, the polynomials are going to be different, but you use exactly the same points. And this is something interesting. And how can you find the polynomials that you need to evaluate to find the dual? Well, this is known as the algebraic dual of the set of polynomials and can be found using this function phi. And let's study this function phi. Well, this function phi is just the addition of the values of the polynomials on the points. Okay, so this function phi depends of the points, of course. And in order to find the dual that you need to, the algebraic dual, which gives you the dual of the code, you are going to find the column between the kernel of this function phi and the polynomials that you are using to construct the evaluation code. And this notation here means that you are going to use the standard monomials, which is not very important now. I just wanted to be precise for the reason I wrote this formula. But the point is that you are using, if you are related to commutative algebra, you are finding here the footprint of the vanishing ideal. Well, again, the important thing for me that I would like that you remember is that the dual of an evaluation code is an evaluation code again. You use again the same points, and the polynomials that you are going to use can be found using commutative algebra tools. This is not too complicated. Okay, so this is for the dual of evaluation codes, and let's focus. Let's focus on monomial codes. What are the monomial codes? Well, let's see what is the meaning of this notation. Well, this notation means these points here represent monomials. And the reason is because, well, this point here, for instance, the 0, 0, represents the monomial x to the 0, y to the 0, which is just the 1. This monomial here represents the monomial x. This point represents the monomial x squared, x to the third, x to the fourth. This point here represents the monomial x squared y. This here represents the monomial x, y squared, and so on. So every point here we are working on the plane. Every point on the plane represents one monomial. Okay, and here we have points. Well, a monomial code is coming when the space of polynomials that you are going to use to evaluate is generated by monomials. Okay, so this is a monomial code. The point we are not talking, we have no restriction about the points. There is no restriction about the points, but the space of polynomials is a space generated by monomials. Not every evaluation code is a monomial code, but some of the well-known families are monomial codes. For instance, the Reed-Solomon code. If you remember, for the Reed-Solomon code, you use a set of points to evaluate, and you evaluate on polynomials up to a certain degree. Well, the set of polynomials up to a certain degree is a linear subspace generated by monomials. And how can we find the dual? Well, this is something that is well known in the literature, but I want that you see the idea and how we can extend this idea. Well, let's take these points for the Reed-Solomon code. Let's say that we are going to evaluate on these points of the field. We are working over Z7. Well, it doesn't matter. The point is that we are going to use these points to evaluate 0, 2, 3, 5, and 6. So we're going to evaluate polynomials up to a certain degree on these points. And let's take the case when the degree is at most 2. So this means that the space of polynomials of degree at most 2 is generated by the monomials. They represent the monomial 1, x, and x squared. Okay. And now, how can we find the dual of the Reed-Solomon code? Well, you are going to use exactly the same points to evaluate, remember that the dual of an evaluation code is an evaluation code, and the set of points is exactly the same. The set of polynomials is going to be different, but there is a very nice relation for this case. Because the set of polynomials that we are going to use to find the dual is polynomials up to degree 1. And why up to degree 1? Well, if you count the points, we have 1, 2, 3, 4, 5 points. So we have 5 points. And for the Reed-Solomon code, we are using only 3 monomials. So this means that there are 2 left. And for that reason, because this gap here that we have, because the dual is generated only by these 2 elements, okay? If the gap here is 3, the dual is going to be generated by these 3 elements. And of course, if you want to be more precise, the dual is not only the evaluation of these monomials on these points. You need to multiply by some constants. And these constants are coming from the indicator functions of the points. Again, I don't want to go through the details. There are some constants and they are not too complicated to, well, I don't want to say that. I mean, it's not trivial to find them, but they are well identified. So they are just, they are coming from the indicator functions of the points. Okay, so this is how you can find the dual of a Reed-Solomon code. And what about a Reed-Muller code? Well, for a Reed-Muller code, some people consider this as an extension of the Reed-Solomon codes because, well, you use polynomials up to a certain degree, but now you evaluate on points in several variables. Because for the Reed-Solomon code, we are using points in the field. And here we are going to use points on the plane. So we are going to use again polynomials up to a certain degree. For instance, for this case, we have polynomials up to degree 4. If you want to find a basis for this set of polynomials up to degree 4, well, these monomials are a basis, right? So these monomials generate all the polynomials of up to degree 4. For the Reed-Muller, you evaluate on all the points of the plane. Again, this is just an example for 2 variables, but this can be written for m variables. Okay, I just want to make sure that this is not only for 2 variables, can be seen for more variables. But the point is that you use all the points of the affine space k to the m, on this case, the plane. So you evaluate all these monomials on all these points. What about the dual? How can you find the dual? Well, we're going to use again the same points. As I said before, the dual is an evaluation code where you use the same points. And what about the polynomials? Well, this is something very simple. If you count, so this box here, this blue box, is coming because the number of points that we have to evaluate, okay? And now, I told you before, for the Reed-Solomon code, this gap here, this gap gives you the monomials that you need to use to evaluate. Well, using the same idea, we have here a gap. Well, this gap gives you the monomials that we need to use to evaluate to find the dual. And if you count the points here in the gap, they are exactly the same than the points here, okay? And this is how you can find the dual. Again, there are, well, for the Reed-Muller, there are no constants, but you can extend this idea to a Cartesian code in the sense that instead of using all the points in the plane, you can use only a Cartesian set. And well, using that Cartesian set, this box is going to be smaller and you are going to have here less points, but the idea is exactly the same. You make the box and the gap, the complement gives you the monomials that you need to use to evaluate and to find the dual. Okay. I don't know if there are questions up to here or comments. Well, you can use the chat if you want. So I'm going to continue with this. And so these are the read Euler codes. And now we're going to define the augmented read Euler codes. What is the idea for augmented? Well, for read Euler, we use all these points, okay, to evaluate. So for the augmented, and I'm sorry, all these points and polynomials up to a certain degree. What is going to happen for the augmented? Well, this is the case for the read Euler. For the read Euler, we use polynomials up to a certain degree. And now what we are going to do is we are going to, instead of using only this diagonal here, we are going to augment, we're going to add more monomials to evaluate. Okay, so for that reason, we have the name of augmented. And the points that we are going to use are the same than for the read Euler. We have all the points in the plane. How can you find the dual? Well, it's the same game than before. For the dual, we have the same points to evaluate. And here we have only this square missing. So we have this gap here. So these points are not here. So using those points, those are the points that define that we need to use to find the dual. And this is a very important step. So having control over the dual gives you the chance to create this repair scheme for these codes. So the dual is a key step, and we have control over the dual for these codes. So it's important that for this approach that you know very well the dual. And now, in general, how can you define the augmented real Euler code? Well, this is just this case that you see here is just for the plane. This can be seen for more variables, but the idea is exactly the same. The idea is this is the notation for the augmented real Euler code. So this means that we are going to use all the points to evaluate on the affine space fq to the m. And something important here is that we are going to use a field extension. Okay, so we don't have only q. So now the points that we are using to evaluate, the coordinates are in fq to the t. Okay, so we have an extension of degree t of the final field fq. So this is important. And we have points in the affine space fq to the t to the m. It's better if you see this. And the monomials that we are going to use are just, we have all the points in the affine space fq to the m, fq to the t to the m. And this means that we are going to remove a box. Okay, so it's exactly the same idea than here, that we remove this square. If we have 3 dimensions, you remove a box. And so this is the idea. Okay, it's better. With an example is much better. So you are going to remove a box to define this augmented read Euler code. And what are the parameters? Well, the length is just the number of points that you have. This is just q to the t to the m, because the size of the fields on this case is q to the t, and you have m dimensions. So you have q to the t to the m, which is q to the mt. So this is the number of points that you have. And what about the dimension? Well, the dimension is not too complicated, because if you want to count the dimension, well, it's just the number of points that you have in the affine space minus this box that you remove to define the augmented. Okay, so for that reason, for the dimension, well, we have the number of points that we have in the affine space minus the size of the box. Okay, so this is just the size of the box that you remove. And the minimum distance is just because the footprint bound. This is something that Olaf Gale started. I don't know if Olaf Gale started with this, with footprint bound. Cicero is here, maybe he can help at the end. But I know that Olaf started working with this, and of course Cicero also worked with this affine with this footprint bound. And because the footprint bound is just the length, the distance between this point here and this corner. So this distance that you see here, this is the minimum distance. I know that this is not a very good minimum distance, and actually it's a bad minimum distance in the sense that this is a very small, but this is something interesting because for the repair scheme that we are going to build is not important. So we know the minimum distance is not good, but it's okay. The dual, as I explained before, well, you use the same points for the dual, and the monomials is just a box. Okay, so it's just this set to the m. So the monomials that you need to evaluate for the dual is just the box. That's it. This is the idea. Okay. Now that we have the definition for the augmented reading Euler codes, we want to develop a repair scheme. And remember, let me go back. What is the meaning of a repair scheme? So every point here represents one entry of the code word. So for this example, we have 1, 2, 3, 4, 7 times 7, 49. So the vectors have length 49. So every entry is coming from one of these points. And a repair scheme means that if one entry is erased, let's say that this entry is erased, the idea is that we want to access to the rest of the entries to recover this one, but we don't want to use all the information from the rest of the entries. Okay. This is the idea for the repair scheme. We are going to use the field trace. The field trace is just when you take one element and you add the q powers of this element. This is how you find the field trace of an element. This can be defined in terms of this polynomial. But the important point that it's important that you notice here, that we notice here, we have only powers of q. Okay, so we have only the powers of q. This is important because the field has characteristic q, so this is important. We have only powers of q. And we're going to use something this well-known result. And if you have a basis, you can use the dual basis. Well, there exists another basis. And take a look to this equation. I want that we take a look here. This equation says that one element in the big field, I'm going to call big field the extension. One element in the big field can be seen in terms of the traces of the values of this element times zi. So in other words, in order to know the value of alpha, you just need to know the value of the traces of alpha times zi, the value of the traces of alpha times the elements of a basis. This is what we are going to use. Okay, this equation here. And how can we do that? Well, the first thing is we are going to develop a repair scheme for the case where k is less than q to the t minus q to the t minus 1. Okay, and the first thing that we were studying this, I thought that this was not something good because this looks like a big restriction, but actually it's not a big restriction because this number here, if you factor q to the t minus 1, is of the order q to the t minus 1. So it's not a small number. This is what I want to say. Okay, so this is a huge number and this is a big number. And when you take the difference, this is not a small number. The difference is of the order of q to the t minus 1. So it's not a small number. So we're going to develop a repair scheme for augmented reading Euler codes when we have this restriction. So let's say that we have one point in the code. And let's say, I'm sorry, so we have one point. It's one entry of the code word is erased. So let's say that the entry fp to the star, where p to the star is one element in the affine space. Because you remember, right? When we want to, the points that we are using to evaluate are the points of the affine space. Okay, all the points. So this is one point of the affine space, and the entry using this point is erased. How can we recover that entry using the rest of the entries? Well, we fix a basis of the extension. And this is the key step. We are going to define these are also known as recovery polynomials. So let's take a look to these polynomials because they are really important. So this is the key step. So for every element of the basis, you are going to define this polynomial. And here inside of the trace, you have the element of the basis, zi. And well, these alphas here are the coordinates of the points that is erased. Okay. So these polynomials, of course, depend of the erased entry. Okay. And using these polynomials, it's possible to repair the entry that is erased. And let's take a look closer to this polynomial. So what is happening here is, well, when you extend the trace, remember the trace is given by powers of q. So when you extend, this is q to the 0. So this piece here is q to the 0. And the last one is q to the t. But they wanted to give this expression because you are going to cancel out this guy from the top and this guy from the bottom. And the very first element is just zi. And the rest of the entries depends of xi minus alpha I, but it doesn't matter. So I wanted that you see that the very first entry is zi, and the last one, the power, the degree, is going to be q to the t minus 1. So in other words, the degree in terms of the variable xj is q to the t minus 1, and I think that this is a mistake. This should be just q to the t minus 1. So this negative 1 is not correct. So this is not correct. It should be just q to the t minus 1 because we cancel out and we remove 1. Okay. But something important is we have this restriction that we have here. This restriction that we have k less than this number says that this set is inside of this other set. And well, what is happening here is that this set is going to be inside of the dual, because if you remember, the dual is just a box. Okay. The dual of the augmented read Euler code is a box. And the important thing is that this set here is inside of the box. As this set here is inside of the box, so this means that the polynomials pi, when you evaluate on the points, they define an element in the dual. And oh, I see the mistake. I'm sorry. I see the mistake here. So this t minus 1 is correct. So the mistake is here because the trace is until q to the t minus 1. So this is the error. I'm sorry. So the trace is the highest power is q to the t minus 1. Okay, so actually this is correct. What is not correct is this one. But anyway, the important thing is that these polynomials, the degree of these polynomials is small enough such that when you evaluate these polynomials on the points, you are going to get an element in the dual. This is the important thing. So the degree of these polynomials is small enough. So remember that we have this vector, this code word, and one entry is erased. So when we multiply the dot product between this entry, between this code word and the vectors defined by the PIs while they are in the dual, so we obtain that the dot product is 0. And for that reason, we obtain these equations here. So this means that we have all the elements from from I equals to 1 to t. So they are coming because the dot product is 0. So in other words, you have the dot product is 0 and you solve for the entry that is erased. Okay, so this is what we are doing in this equation. And now we define two sets. So the first set, gamma 1, is the set where at least one entry is the same. And gamma 2 is the set of points where all the entries are different to the erased one. Okay. And well, what is happening here? I wrote again pi. I have the same mistake. This should be q to the t minus 1. I wrote again pi because if you remember, I told you the very first entry is zi. The very first entry is zi, but in the rest of the entries, you have these guys. These guys belong to the rest of the entries and to the rest of the components. And so this means that when you evaluate in one element of gamma 1, well, you are going to get only the value of zi. And so for that reason, you are going to split this sum into two sums. The first one is the value in gamma 1 is always zi. So you have this piece here. And for the rest, I don't know the value, but the important thing is that here, I have the value of the trace, only the value of the trace. And so the repair polynomials pi are important because now, if you see, here we have an element just of the trace. And this is important because if now we apply the trace function to all these equations, or to the last equation, when we apply the trace function, what we are going to get is, because this is a trace, because this is an element of the small field, when you apply the trace function, you can take this element out. This is the important thing. Well, everything is important. This is a key step. So for that reason, we have this element here. And what is happening from this equation? Well, what is happening is that here inside of the trace, you have FP. And this FP, the trace of this entry, is what you need to recover the element. Okay, and because this is for all the for I from 1 to t. So if you remember, knowing these values, if you know these values, you are going to be able to know the value of this one. Okay, in other words, in order to know these values, what you need to know is the value of the trace of this element, FP, what we have inside of the parentheses. Okay, so let me check what else we have. We have that as a consequence, in order to recover the erased entry, well, you need to know the values for some points and just the trace of other values. Okay, so this is the idea. And maybe let me give you an idea of what is happening here is, let's say that we have this augmented reading Euler code. So we are using these monomials to evaluate, and we have all these points. Remember, every entry defines an entry of the code word. Every point here defines an entry of the code word. So let's say that the entry associated to this point is erased. Well, the previous scheme that we developed before says that in order to recover this entry, you need to know all the values, the full values. I mean, by full, I mean the element in the big field on this line, the elements on the big field of this line. But for the rest, you don't need to know the full symbol. You just need to know the trace, which is just an element of the small field. Okay, so this means that if these entries belong to f to the 8, well, you need to know all the symbol here, but here you just need to know the element of f to the 8 as f2 vector space has dimension 3. So you need to know only one of those 3 dimensions. Okay, so that is the idea. So this is the trace. You need to know the trace value for these points. In a code word is composed. So we have 64 entries. F8 is a 3 extension of F2. Okay, so this means that every code word is composed by 192 subsymbols. And using this recovery scheme, you can recover an erasure using 91 subsymbols. So this represents the full symbols here, and one subsymbol for the rest of the code, for the rest of the entries. And this is something interesting because the Reed-Solomon code is always bounded by the size of the field. And here we don't have that restriction because we have several variables. So we don't have that restriction. And even more, when you use Reed-Muller, no augmented, when you use Reed-Muller, we know that the rate goes to 0. But for the augmented Reed-Muller codes, the rate is non-zero. And you can play, actually we played and we developed another augmented Reed-Muller code. And for that augmented, the rate is exactly 1, which is great. And this number that you see here, this number 0, is the portion of the code word that you need to download. So in other words, here for this example, for this particular example, you need to download 91 subsymbols out of 192. So in other words, you need to download almost the half of the code word, okay? But this, if the extension is greater, the part of the subsymbol that you need to download go to 0. So this is something that we didn't expect, but it's happening for the augmented. Even when the dimension is huge, you need to download only a very small piece of the code word. And that's it.